Hello, everyone. So in this video, I'm going to talk about a relation between some lines. Okay, and then we are going to name it PowerPoints. So in some books, you may see different names, but I like using PowerPoints. Okay, so let's go ahead and start with the first case. We have actually three different cases where we are going to actually see a different relation when you have some lines. Let's take this as our circle. And the first case where you are going to have two chords. Let's say this is my one chord and I will have another chord. So if you have two chords are intersected inside of the circle, okay? And then I'm going to call this is C and D. And we have a relation between these segments. I'm going to maybe call this is K, okay? And but I don't want you to just memorize, so which is why we are going to actually use it a similar triangle, like to get that actual relation. So, and in order for us to really understand this one, we need to have some sort of background about the inscribed angles as well, which is something I will kind of ask you to look into if you don't know anything about it. So if I connect these two points, I will get a triangle right here. And if I connect these two, right, and I will get another triangle right here as well. So in this case, the angle at C, vertex at C, is subtended by this like arc BC, I mean BD. And the same idea is actually right here. So the angle arc, inscribed angle A, inscribed angle A is also subtended by the same arc BD, which is why angle A and angle C has the same angle measure. That's one thing. And the same thing with this guy. So the angle D is subtended by arc AC, and B is also subtended by arc AC, which is why those two angles are also equal, which is enough for us to say this triangle and this triangle are similar, but we also know these two angles are equal because they are vertical. So we have three pairs of angles in these two triangles are actually congruent each other, which is enough for us to say they are congruent, they are similar. So let me write that as well. So the triangle ABD, ADK or AKD, whatever. So I'm gonna go with ADK, K is similar to, since I start with A, so I should go with C. So the triangle C, and my second was D, so this angle same as B, so I should go with B, and K has to be corresponding one. And they are similar by angle, okay? So that's the reason. And if they are similar, then corresponding sides are proportional. So let's write that. But at the same time, I don't want to use AD and BC because that is the two segments that I actually added. That wasn't part of the actual figure, which is why let's not use that two sides. So if I take a look at this green angle that is opposite to like DK, so I'm gonna go with that, divided by the same angle C is opposite to BK. So I'm going to call BK. That ratio has to be equal to this angle is opposite to AK in the first triangle that we start with. And the same angle right here is opposite to KC or CK. So this is the relation. If you really want to do cross multiplication, we can do that. So that will be AK times BK is equal to CK times DK. So again, this is the first relation, but I really want you to understand what that looks like, right? So it's basically AK, BK. So the part of this chord, like AK and BK, when you multiply those two pieces, that will be equal to DK times KC or the CK. And that's the first relation, okay? And I will say this is the between like this is the intersection of the two chords. Okay, so we have two chords, and that's the first case. Okay, I'm gonna maybe call case one. Okay, so two chords. Okay, that's the first one, and the second one. Okay, let's do that. Case two, and I will take another like case where we are gonna have a little bit different picture. Okay, so let's try Okay, that's not a circle for sure. So if I take this my circle, and in this case, I'm gonna take a segment where gonna cut the circle into different points. So if I take that point outside of the circle, in this case, the intersection of those segments were inside. And in this case, the intersection of these two segments are outside, okay? And I'm gonna call this is P, let's call this is A, B, maybe C and D, okay? So now we do have this picture, but if you remember, we did some similar triangles. We were able to find some similar triangles when you extend some segments, but I don't see anything like easier like this in this case, right? But I do need to have triangles so I can actually have some similar triangles. So what I'm gonna do, I'm gonna connect A and C. Okay, so and then I'm gonna connect B and D. Okay, so now I do have two triangles. But at the same time, at this moment, we probably need to remember some of the angle properties of the circles. So if you remember this angle, let's say, let's show this guy, the an ACBD, like ACDB actually, this is a quadrilateral in a circle, and an ACDB, all those vertices are on the circumference of that circle, and we call this is cyclic quadrilateral. If you have a cyclic quadrilateral, the angle right here and the other side, which is angle A, is add up to 180 degrees, which is really easy to prove it. So if you remember the inscribed angle relation, you can just take a look at that. So if this is alpha, then this guy will be right here will be 180 minus alpha. I'm gonna call this is alpha, and this is 180 minus alpha. The opposite angles are supplementary. But we know this is a straight line, which is why this guy right here, the what's remaining from that straight line is gonna be just alpha. Okay, I hope you can see what I'm talking. So now in this triangle, PAC, we have alpha and this alpha, right? So we can just write these two. And also we know the angle P in this triangle PAC and PBD is also having the angle P as a shared angle. So we have two angles are equal. So if you really want to make a figure like this, I will just actually split it so we can kind of see it. I'll just draw this one. So let's say this is the smaller one, and I'm gonna assume this is the larger one. Okay, so this is P, and I have A, C, and I have B and D. So in this case, we did have the angle, this was alpha, and this was alpha. And also we already know angle P's on both triangles are equal, so I can share the same thing. So that means C and B has to be same. So which is why these two triangles are also similar by angle, the same reason, okay? So we just wanna write the ratios. Let's do that. And if I do, like, I like to start with not A, C, and B. I don't wanna use those because those are the two additional stuff that I did. So it wasn't part of the actual problem. And if I start with maybe AP, which is opposite angle C, okay, AP, over angle C is same as this, which is opposite PD, okay, is equal to, and I can go with now PC, which is opposite to alpha, so that's PC. Alpha is opposite to PB. So if you do a cross multiplication, so I'm gonna kind of write here, so AP times PB is equal to PC times PD. And this is our second relation. Okay, so it's kind of the same as this one, but it's a bit different. So let me try to help you a bit to understand what's going on. So AP is the distance between that point to the first intersection with the circle. PB is the distance between the point with the second intersection. So this distance times this distance is equal to this distance times this distance. So if you kind of remember such a like way to remember, so it will be a bit easier to do so. And this is the second case where you have two secant line, okay? And when you have two secant line is basically the line that cutting the circle into different points. And we do have this relation. And then we have a third like case, which is one of them will be secant line while the other one will be a tangent, which is actually something I'm gonna leave you as a challenge to see if you can find a relation like this, and I will maybe do that in the next video. Okay, I hope that was clear. I'll see you in the next video.